Okay, so in the last two lectures, we were not able to use the projector. Thanks for bearing with me, but looks like they got the projector fixed. So I'll just summarize what we had learned in the last two lectures, and then we'll move on with the new concepts. Of course, our labs are going to start on September 15th. So if you have still not ordered your components, please go ahead and do so. They take maybe 1 week or 10 days of time in the worst case, but make sure that you are ready with all the components before the first day of the labs. That is 15th of September. That would be a Monday, 15th September. So it's there on the Canvas page. So let's see. So for example, the lab one notes are already uploaded here. That what you need to do, the documentation is there. You can go ahead and read it as well even now, but the labs will actually start on September 15th. And I'll ask the UPIs to hold maybe a 1 hour lecture session before that, so that you know what to expect from the lab sessions. So basically there would be a pre-lab and an in-lab section. The pre-lab section is something that you have to do or you have to complete before you get to the lab. So Monday, September 15th, whoever has the lab on that day, please make sure that you complete your pre-lab section before you get to the lab. And once you're in the lab, your TAs or your UPIs will ask you to perform some of the experiments, and your in-lab grading will be based on that. Remember that pre-lab is 80% of the grading, whereas in-lab is only 20%. So make sure you do your pre-lab sections carefully before you actually go to the lab. All right. Okay, so these are the slides that we were discussing in the last two lectures. We have looked into voltage and current divisions. We have looked into amplifier gains. We have looked into these example problems of how to solve voltage gain and current gain. And we have started looking into amplifiers as well. You know how the ideal op-amp looks like. What are the properties of the ideal op-amp from your 3111? In this class, we'll be focusing more on real op-amps, which means that you'll have a finite input resistance, which is over here on your screen. You have a and finite input resistance, which is not, of course, for an ideal scenario, you'll have infinite resistance at the input. In a real scenario, you have these input terminals, the plus and the minus terminals of the op-amp, and you have a finite resistance between those two. You also have a non-zero output resistance. So remember, this is also part of the op-amp itself. So this triangle that you see, that is basically what your op-amp is, right? If I go back one slide, that's basically what your op-amp was. And then in the ideal scenario, you had infinite impedance at the input, zero impedance at the output. And the job of your dependent current source was to multiply the differential input voltage, which is V1 minus V2. Okay, or in this case, V2 is connected to the positive terminal, so it's V2 minus V1. Okay? Depending on what is connected at your positive and what is connected at your negative, you can figure out that what would be your output. All right. Now, with that, you'll see that there would be a voltage division at the input side between the RS resistance, which is a non-ideality of the source, and the Rin of the op-amp. So you have that voltage division here, Rin divided by Rin plus Rs. You have AV0, which is the voltage gain of the op-amp if the input is Vi. So remember, your input may not be, even though you're providing this Vs as your input voltage source, the op-amp might not be seeing that entire voltage because there would be a voltage division at the input between Rs and Rin. So what you see is this Vi voltage, and Vi is nothing but Rin divided by Rin plus Rs times Vs, because of the division between the two resistors. Then you have this AV0, which is the gain of the op-amp. Again, for a real scenario, it's not infinite. It will be a finite number. And then you have a voltage division at the output between Ro and Rl. And this is what you see at the final output across Rl. Across Rl, you have Rl divided by Rout plus Rl. That's the voltage division ratio at the output. And that's what you see here. Now, once you see this, you'll know that for an ideal op-amp, again, why do we want infinite input impedance? Because if your Rin is infinitely large, this first term, this first term over here, that becomes that ratio becomes 1 because Rin is infinitely large. So Rin divided by Rin plus Rs will become equal to 1. Similarly, you want Rout to be equal to 0 for an ideal op amp. And in that case, this term, this voltage division ratio at the third term here, RL divided by Rout plus RL, will almost be equal to 1 if your Rout is 0. So that's why you can just directly understand this, that how it what the implication is in terms of a real versus ideal op amp, that you want your Rin to be infinitely large and Rout to be infinitely small. And this is the reason. You want to stop those voltage divisions. And that's why you want to design even your real op amp with a very high input impedance and a very low output impedance. Okay. Next thing that we are going to quickly look at is Thevenin's and Norton's theorem. Again, this is just a recapitulation. So what Thevenin's and Norton's theorem tells you is that if you have a circuit which is kind of like a black box, so let's say, for example, if I go back 2 slides over here, and let's say that, yeah, this is, okay, let's change the color. Okay. So let's say this is my black box, which is my op amp. Right? So I don't care what is inside my black box. How do I know that if I connect a load resistance over here, what would be my voltages and effective resistances looking into that black box? That's what your Thevenin theorem will tell you. And Thevenin versus Norton, they are just duals of each other. Whatever is in a voltage domain is called Thevenin. Whatever is in a current domain will be called Norton. So they're just duals of each other, as you have learned in your 3-2-1. So how to sort of model your Thevenin and Norton's theorem? Again, just a brief recapitulation. You have your black box over here. You want to find out what is the open circuit voltage across this black box on the output side, and that will be called your Thevenin voltage. And you also want to find out your Thevenin equivalent resistance. For that, what you can do is that you can connect, let's say, for example, let's look at the middle plot over here, or the diagram in the middle, that you connect a test voltage. You connect a test voltage at the output side, and you look at what is the current going into the black box from the output side. The ratio of your V test over I test will be your Thevenin equivalent resistance. So whatever voltage you connect here, and you look at the current, the ratio of that voltage to current will give you resistance, and that's the Thevenin equivalent resistance. What is most important to remember here, that while you are doing so, while you are trying to calculate the Thevenin equivalent resistance or the Thevenin equivalent voltage, you want to make all the independent voltage sources inside the black box or anywhere else connected on the black box or in a circuit diagram. You want to make all the independent voltage sources 0, and you want to make all the independent current sources an open circuit. So short all your independent voltage sources and open all your independent current sources. Why do you want that? Because you are already connecting a voltage source over here to calculate something. If there are other voltage sources or current sources in the circuit, they will interfere with what you are trying to do, because 2 voltage sources will somehow interact with each other. A current source and voltage source will want to interact with each other. You don't want that interaction, because that will create errors in your calculation of your Thevenin resistance. You just want the passive value of the resistance. You don't care about what other, let's say, energy generating component connected in the circuit. And that's why you short the voltage sources, you open the current sources. Remember, they have to be independent ones, which means that if there are dependent current or voltage sources, they will also have almost no effect, because the independent ones are already gone. So the dependent voltage or current sources effects also goes away if they are dependent on the independent voltage or current sources. Okay, so this is just one way to do it. Again, as I said in the class in the first lecture, there are multiple ways to solve the same problem in electronics. So instead of connecting a test voltage, what you could have done is that you just connect a test current over here. And I know that many of you will feel more comfortable connecting a voltage source than a current source in a circuit. And that is perfectly fine. That's why I discuss this first, where you are connecting a test voltage source and measuring the current coming out of it. But some of you might also find it more intuitive to connect a current source in the circuit and measure the voltage across it. And it does the exact same thing. So you have a current source, a test current source connected on the output side. you measure the voltage across it, the ratio of V test and I test will again give you the same Thevenin equivalent resistance. And if you do the analysis in this way, you will see that you will get the exact same Thevenin equivalent resistance, however, whatever is the method of your analysis. Okay. All right. So this black box can now be represented as a Thevenin equivalent circuit with a Thevenin equivalent voltage and a Thevenin equivalent resistance connected in series. The Norton equivalent will be the Norton equivalent current and a resistance connected in parallel, which will be the Norton equivalent resistance. We'll look at an example to understand this better. So for example, if your actual circuit looks like this, you have a VO, let's say that's your source. Then you have this R1 and R2. Let's say a very simple resistive network. You already know how to solve it, but still just to understand how Thevenin or Norton works, we will try to solve it using the Thevenin equivalent circuit or a Norton equivalent circuit. So let's say you want to find out what is the voltage Vx across this output port, the port on the right-hand side. What is a port? A port is a combination of two terminals, right? So in a circuit, you might see multiple terminals or nodes. You have already done nodal analysis in your 3111. So you know what a node is. It's basically a terminal on the circuit. So let's say you have a positive terminal here and a negative terminal here. The meaning of positive and negative is just that you want to calculate the voltage from the positive to the negative, assuming that the positive is the higher voltage and the negative is the lower voltage. It may not be so. In that case, the value of your voltage will be negative, right? So that's just nomenclature and nothing else. So you have a port on the right-hand side, which is a combination of two terminals. So a port means two terminals. One of them will be a positive and the other one will be a negative terminal. The Thevenin equivalent circuit for this is something that looks like this over here. So looking into the same port, you'll see the Thevenin equivalent resistance, which is the equivalent resistance you see here. What would be the equivalent resistance? If I just do a simple bit of math, you know that when you are trying to find out what the Thevenin equivalent resistance or the equivalent resistance at the input or output, first thing you need to do is short out the independent voltage sources. So just short this out. The voltage source does not exist for you anymore. And then what do you see? You see R2, and in parallel, you see R1 connected here. Why do I say that the R1 is parallel to R2? Because now, because the voltage source is shorted, the top terminal of both the resistances and the bottom terminal of both the resistances are same, effectively the same, because the voltage source does not exist anymore. And that's why you have R1 in parallel with R2 as your equivalent resistance. Right? That's your Thevenin equivalent resistance looking into the port. What would be the Thevenin equivalent voltage? Again, this is just a brief recap of what you learned in 3111. The Thevenin equivalent voltage looking into the port. So looking into the port, what you want to see is what is the voltage that I see between these two terminals. You don't care about what was the original voltage. The original voltage was part of a black box, right? So you don't want to know what is there inside the black box. You want to know what you see at the output terminals of the black box. So what do you see at the output terminal of the black box? You will see only the voltage across these two terminals. You will have no idea what is there inside the black box in a Thevenin equivalent model, right? So what is the voltage that you see at this terminal? Of course, there will be a voltage division between R1 and R2. The voltage that you'll see will be the voltage across R2, right? That's the resistance that you see on the output side. So your voltage across R2 is VO times R2 divided by R1 plus R2. And that is going to be your Thevenin equivalent voltage. Okay, now why is this useful? We'll learn that if we'll take a look at an example. Let's take an example of an audio microphone system. Many of you are interested in the audio engineering club, and many of you are already part of, I believe. So let's say you want to create a microphone network. So basically an audio amplification system. But you know that the voltage coming out of the mic is generally very small. So even though I'm now, my voice is getting amplified, what is actually going into the mic is a very small amount of voltage through some kind of a piezo transducer. And let's say that voltage being generated is only about 10 millivolt or so. And after that, you have let's say some kind of a network inside the microphone. And then you have a load across which you'll measure the voltage. And then you'll have an amplifier to amplify that voltage. Why would there be a network? Now, in this case, we are kind of oversimplifying the network, but there could be filters inside the microphone, which will create different amount of impedances for different frequencies and so on. So this is just an oversimplification of what is there actually inside the microphone network, but just to give you a feel of what could be a real system. That's why we are showing this. So let's say there is a microphone network which looks like this. The input resistance of a typical audio amplifier is about 50 kilo. So let's say you want to amplify. So let's say you want to amplify the voltage, whatever voltage you see or you collect from the microphone, going through the microphone network, and then being available at the input of the amplifier. And you can again assume that this is just an op-amp. This is the positive terminal, this is the negative terminal. So looking into the op-amp, if it were an ideal op-amp, you would have seen infinite resistance, infinite impedance, right? But real systems will not have infinite input resistance. And this is an example of a real input resistance of a typical audio amplifier, only about 50 kilo ohms. So looking into the audio amplifier, you'll see a 50 kilo ohm load. And then the amplifier will amplify this. So maybe you'll get a 1 volt at the output, right? So 1 volt peak to peak at the output. Maybe you'll get that, right? We are not going into that right now, but that's what we are trying to do here with this example. All right. So that's why as the load, I'm drawing a 50 kilo ohm resistance. That's it. That's what I see looking into the amplifier. And this becomes my network. You want to find out what is the voltage that is developed across that 50 kilo ohm resistive load, because that's what your op-amp is going to see. That's what your audio amplifier is going to see. Okay. How to solve this? So first thing that you do, again, as you have done in 3111, that whenever you're trying to analyze something using Thevenin's or Norton's, the load does not matter. The load could have been anything. And that's what you'll analyze later on by putting that load back to the black box. First, you want to have an idea about what is the black box. Okay. So the load does not matter if only thing that you are now concerned is the black box. The load is separately connected to the black box. So first thing you need to do is disconnect the load. So get rid of the load, you have this circuit. Now you'll want to find out the Thevenin equivalent of the remaining circuit. And by Thevenin equivalent, I mean both the Thevenin equivalent voltage and the Thevenin equivalent current. And then you reconnect the load back. So right now the circuit looks like this. This is kind of, let's say, complicated. But what you eventually want to end up with is basically a black box. And you want to find out that if this is my output terminal of the two terminals of the black box, that is the output port, you want to find out what is the voltage that you see at the black box and what is the equivalent resistance that you see looking into the black box. And that will model your black box as a voltage source in series with a resistance. So this voltage source will be your Thevenin equivalent voltage source. And this resistance is going to be your Thevenin equivalent resistance. So that's what you model. That's how your model of the black box will look like. Now, if you reconnect the load back, so you'll just reconnect the load back here. So this is RL. Right? So now you again have a very simple circuit, a Thevenin equivalent voltage, and then a voltage division between the R Thevenin and RL. And eventually you want to find out what is the voltage developed across RL. That's your job. And that's what we are going to do using the Thevenin equivalent circuit for this microphone network. So first thing we did, disconnect the load. Second, you want to find out the Thevenin equivalent resistance, and for that you'll set the voltage source to 0. So because this was an independent voltage source, set the voltage source to 0, short it out, and find out what is going to be your Thevenin equivalent resistance. What is going to be your Thevenin equivalent resistance if you're looking from the output port? So this is where you are trying to look at. What do you see? You see a 10 kilo ohm R3 first, correct? You'll see a 10 kilo ohm R3. Then what do you see? You'll see a parallel combination of R2 and R1. Why do I say that it's a parallel combination? Again, because the voltage source is shorted, your top terminal of the R2 and R1 is same. Also, the bottom terminal of the R2 and R1, both the resistances are same. And that's why R1 and R2 are in parallel with each other. And then you see this R4 resistance. So basically you are trying to go from here, traverse the entire loop and come back through here. Right? That's what you're trying to do when you're trying to look at that Thevenin equivalent resistance. So you have plus R4 because R4 is in series. You just put the numbers. I'm not going to do that number calculation right now. it will turn out to be 43 kilo. So you have a Thevenin equivalent resistance of 43 kilo ohms. Any questions?
Can you talk that as Thevenin current and then a parallel Thevenin?
You can, that will be called the Norton equivalent circuit. Right? So whenever you go in the current domain, so Thevenin and Norton are, even though they were different people, they actually did the same thing and said, oh, see, I'm doing something different. They did not. They did the same thing and represented in a different way. One looked at the voltage domain, one looked at the current domain. That's it. So now whatever you are more comfortable with, do that. And I'm generally more comfortable with it. I like that guy. Okay. All right. Okay. So now what would be your job? Your second job would be to find out the Thevenin equivalent voltage. We just find out the Thevenin equivalent current, Thevenin equivalent resistance, but we did not find out the Thevenin equivalent voltage. So to do that, again, you are analyzing the circuit in a no load condition. Remember that we haven't yet put back the load. You want to find out the voltage across that port terminals, output port terminals, and that would be your Thevenin voltage. How do we find that out? So this was your circuit. Again, remember, no load is connected. So if there is no load connected, the only loop that is present in the circuit is the left-hand side one. The right-hand side loop does not exist. So if you had the load connected here, then there would have been two loops and there would be, the circuit would have been more complicated. There would be a current division from here, and then there would be currents in both the loops. That would have been the case if you had the load connected, right? But Thevenin makes your life simpler. It gets rid of the load first. That means that there is no loop on the right-hand side. There is no current flow through this open circuited resistance. There is no current flow through this open circuited resistance. There is only a current flow in the inner loop, which is here. That's it. Okay. So what is that voltage that you developed across this R2 resistance now? That voltage that you develop across R2 resistance, that is the Thevenin equivalent voltage, because in absence of no currents here, the voltage at this terminal is same as the voltage at this terminal. Again, in absence of no current here, the voltage at this terminal on the far right side bottom is same as the voltage at this terminal over here, according to Ohm's law. If there is no current, voltage drop is zero. So the Thevenin equivalent voltage is just a voltage division between this 100 kilo ohm R1 and the 30 kilo ohm R2. That's it. R3 and R4 has no effect on the Thevenin equivalent voltage because there is no current flow through R3 and R4 because there is no load. Okay, so your voltage, Thevenin equivalent voltage, becomes a voltage division between those two resistances, R1 and R2, and that is equal to 2.3 millivolts. Note that there is no current flow through R3 and R4. That's again a very important consideration. Any question on the Thevenin equivalent voltage? Okay, now that you have both the idea about both the voltage and the resistance, we are going to just consider the Thevenin equivalent voltage of 2.3 millivolt because that's what our black box gives us. You want to connect the Thevenin equivalent resistance, which you calculated to be 43 kilo, because again, that's what our black box gives us. And then you connect back the load. Your load was 50 kilo. That's the input resistance of the audio amplifier. Now you have a simple voltage division once again. And that voltage division will give you 1.24 millivolt as the final answer that is available to your audio amplifier. Okay. All right. What are the limitations of Thevenin's? I'll not go through Norton's equivalent circuit once again because, again, that was part of your 3111. I'm assuming that you would be able to do the same thing if you are asked to do with the Norton equivalent circuit as well. So what are the limitations of Thevenin's and Norton's? We have to understand that, okay, this is a good tool, but does the tool work all the time? And the answer is no. These are only appropriate for circuit elements which are linear. So we are, and in the first lecture, we are talking about linearity of op-amps, right? That you want your output to be a linear function of the input. Where does that happen? It happens for a resistor. For example, let's say the current through a resistor is a linear function of the voltage of the resistor. Right? Capacitors, inductors, etc. So these will not work with circuits that will have diodes or transistors. We'll learn about diodes or transistors in this course. And diodes and transistors will not follow Thevenin's and Norton's equivalent circuits because Thevenin's and Norton's equivalent circuits are only applicable for passives and only applicable for linear passives. They will also not work for unilateral system. What is meant by unilateral versus bilateral? Think about a resistor. Oops. So what is a bilateral circuit? So think about a resistor. If you apply a voltage of 1 volt like that, let's say I apply a 1 volt between the left side terminal and the right side terminal, I'll have some current flow from left to right. On the other hand, if I had applied the same 1 volt resistance, from right to left, so your positive terminal is the right hand side, negative terminal is the left hand side, you will have the same current from right to left. So the resistor is a bilateral element. However, the way you connect the voltage, the current through it, the value of current remains same, the direction changes. Same does not happen for a diode. We'll learn about diode in this class. Same does not happen for a diode. If you connect your voltage here versus here, the current that you see will be very different if you connect your voltage here versus here. So this current and that current, so let me draw it in a different way. Let's say double arrow over here. So the double arrow current is different from the single arrow current. So this is an unilateral element. Similarly, MOSFETs, BJTs, there will be unilateral element, and Thevenin and Norton equivalent circuits are not applicable for them. Also, if there is a magnetic linking, if you are doing a, let's say, inductive power transfer, then also Thevenin and Norton equivalence does not hold true, because the currents in the two parts of the magnetic linking, of course, they will be linked magnetically, but they will not be linked by circuit elements as you see in the Thevenin and equivalent Norton equivalent circuits. Yes.
So we say magnetic linking. Does that imply that we can use Thevenin Norton for AC circuits that just have like resistors about that?
Yeah, if it is let's say just resistors, capacitors, you can always use Thevenin and Norton equivalent circuits for AC as well. It does not matter whether this is a DC voltage or AC voltage, right? The same AC or DC currents will still be linked to the value of the voltage or value of the resistors in the same way. Right? The voltage source or current source does not matter. It matters what are the other components here. And in this case, when you have unilateral linear components, your Thevenin and Norton equivalents will hold. Okay, so one thing that I want to discuss before going into a little bit more details about amplifiers is whenever you're doing circuit analysis, always keep in mind why you are analyzing the circuit. What do I mean by that? Let's say, for example, the thing that we just talked about, that, okay, for a unilateral circuit versus a bilateral circuit, the currents and voltages or the Thevenin equivalence or Norton equivalence may have very different implications. So always remember, what is your goal eventually? Do I want to amplify an AC? Do I want to create a different DC voltage out of it? Do I want to convert AC to DC? Or do I want to just convert AC to AC, but at different power levels or different voltage levels? Depending on that, your circuit topologies will change, your circuit architectures will change, and the elements that you'll be using in the circuit will change. So everything depends on eventually what is the application that you are trying to look for. And the purpose of this course, or what we'll try to learn in this course, is design-oriented analysis, that will keep the final design in mind, that this is what we want, this is the specification that we want to achieve, and we'll work toward that. Of course, that would also mean understanding the elements properly. So whenever we are doing a mathematical analysis, 100 kilo ohm resistance means 100 kilo ohm resistance. But in real life, if you go to the lab, pick up 100 kilo ohm resistance, it may not be 100 kilo. The 100 kilo ohm resistance that you pick up versus the 100 kilo ohm resistance that you pick up may be different values. So how do you take care of those non-idealities when you are trying to design circuits? That's what we are going to try to learn in this particular course. Okay. Right. So before I going into amplifiers, I would quickly like to go through the homework 1 problems once more. I did that in the last lecture as well, but we did not have the projector at that time. So your homework 1 problems have been uploaded. I know initially the deadline was this Monday, but then I noticed the Monday is a holiday, right? So I'm going to move that deadline to the Wednesday. So please complete your homework 1 by Wednesday and submit on Canvas. It's already active. You should be able to see that. And I'll make the change. If you look into Canvas now, you'll still see the deadline is Monday, but I'm going to change that to Wednesday. Question?
Yeah, were there problems from the book you wanted to do as well?
Sorry, could you please repeat the question again?
Were there problems from the book you wanted us to do as well?
For practice, yes. I think I provided a few problems that you can practice.
Yeah,
Like, yeah, that was probably 3 pages worth. But if you're already comfortable with like some voltage division, current division, Thevenin Norton, you don't need to do it. But it's just that if somebody is not yet comfortable with these concepts, please make sure you practice. The more you practice, the better you'll become at this. Okay. So that's why I have also posted these some of these example problems from Cedar Smith and their solution. And solutions are probably just 1-liners, 2-liners, and so on. But there are problems on voltage dividers, current dividers, Thevenin equivalent, circuit analysis, and so on. So if you want to get better at this, please make sure that you go through some of these practice problems. They are not graded. You don't need to submit or anything, just for your own practice. All right. Okay, so I'll change the deadline. It will become September 3, Wednesday, same time. Please submit it before the deadline. Now, going back to the problems. Of course, as you see that the first problem is a very simple voltage division problem. Second problem is also very similar, just the resistance values are different. The third problem is a current division problem. Again, something very similar to what we solved in class. The fourth one and fifth one are probably a little different. That, okay, now you have an amplified equivalent circuit. We'll take a look at an example today, right now, in the next 5 minutes, and that will tell you how to solve the problem number 4. Many of you already have a sense of how to solve it because we discussed that in the previous lecture on the blackboard. Problem number 5 is also an amplifier, right? So if you see here, this is basically your amplifier, this black box. Again, here, over here, this black box is your amplifier. So you have your amplifier black boxes. You have the input resistance, which is the series resistance, the non-ideality of this guy, this source. So you'll have a voltage division between these two resistors. And whatever voltage you see here between these two terminals, that's your input voltage to the amplifier. The amplifier amplifies that input voltage, this Vin. The amplifier does not amplify Vs. Keep that in mind, because Vs, the amplifier does not even see Vs. The amplifier only sees Vin, which is a voltage division between Rs and Rin. So amplifier will amplify Vin, and the value of A is given to be, let's say, 100. Again, just an example. And then you'll see a voltage division at the output side between Ro and Rl. And then you'll have the final output voltage. So that's your homework problem 4. Homework problem 5 is also exactly similar, but don't get confused by the fact that there is a current source now. So this was a dependent voltage source. This is where we are representing it as a dependent current source. Interesting to note is that the value of the dependent current source, as you see in the previous case, it was A times Vin. So this was a voltage amplifier. The model was a voltage amplifier. Your output is voltage, your input is also voltage. And the ratio of those two voltages is the voltage gain A. Here, you're creating a current which is dependent on the input voltage Vin. Input voltage Vin is still the same, the voltage developed across the input terminals of the op-amp. But you're generating a current, so your output is current. So what is your transfer function? If your output is current and input is voltage, the transfer function is a transconductance, because current over voltage is a conductance. So GM, that's basically is going to be called your transconductance. GM is called the transconductance, and the value of GM is 1 milliampere per volt. Here, A was a unitless quantity because it was voltage gain, voltage over voltage. GM has an unit. It's current over voltage. And current over voltage, you can, in this case, it's represented as milliampere per volt. Books might say that, yeah, you can represent it as Siemens, which is ampere over volt. You can represent it as ohm inverse, or sometimes you might see it as mho as well, because you write OHM and write it opposite way, it becomes MHO. Right? So that's why there are different terminologies, but they all represent the same thing. It's transconductance. Okay. Now, as you know that just like the voltage source will have a series non-ideality, a series resistance as its non-ideality, a current source will have a parallel resistance as its non-ideality. So this is just the model of this current source altogether. So let me just draw it with a different color. For example, this was your voltage source, the AV in and this, let me clear everything up. AV in and this RO together, that's basically the non-ideal model of the dependent voltage source. The current source and the parallel resistance is just the non-ideal model of the dependent current source. And that's it. Again, Thevenin inverse is not an equivalence. Your series resistance becomes a parallel resistance and so on. Okay, and then you connect a load over here. But remember that you're asked to find out the voltage output. So even though this is a current, you're asked to find out a voltage output. So what you can do, looking here this side, you'll see a parallel combination of these two resistances. The current multiplied by the parallel combination of these two resistances will give you the voltage at this point, right? And that is the same voltage that you see at this point. So just find out what is this output voltage over here. Remember that we're not asking the current at the output, even though your amplifier model is a current amplifier or the output of the amplifier is current. Question?
A hypothetical, but in 4, where would like a resistor connecting the input and the output go?
If there is a resistor connecting the input and output. What you're talking about is a condition that, let's say I have some kind of an amplifier, and let's say I have connected a resistance between the input and output. Is this what you're talking about, right? So of course, depending on, we'll go into much more details about these models as we go further in the course, but depending on which terminal is what. So let's say this positive terminal is indeed the positive terminal of the op-amp, then this resistance over here in your, let's say, some transistor or some kind of an amplifier model. Of course, this is not the exact model that we wanted to talk about, but that resistance will be between these two terminals. Or let me draw it in a better way. So this input terminal is accessible. The output terminal is accessible at this point. So you have your resistance, and this will be connected back here. So maybe your question, that's a very good question, because what you're asking is that this terminal, the right-hand side of this resistor, is it this terminal or is it that terminal? And the answer is, it will be this right-hand side terminal. Why? Because you don't have access to the inside of the op-amp. This is totally inside the op-amp. The dependent voltage source and the non-ideal resistance connected to it is totally inside the op-amp. You don't even have access to this terminal. So that's a great question, actually, just to understand the topic, that, okay, you have your resistance over here, and the resistance can only be connected to the right-hand side terminal of this RO resistor. Any other question? Yes.
For number 5, the dependent current source is facing down.
Great question. Exactly. So this will make, so the current is facing down, which means that we are expecting the current to go in this direction. However, you are asked to find out the voltage output, assuming this is the positive and this is the negative, which would require the current to go in the other direction. So according to nomenclatures, the voltage value that you finally find out will have a negative something. So it will be negative and then something that you find out, because the current direction is opposite. But had the current direction been in this manner, then of course the output voltage would have been positive. Yes. Sorry, let me check that once again. So notes file for lecture 1, this one. Okay. I'll just update it. Thanks for mentioning this. So if you see any kind of issue with Canvas, please feel free to drop me a note either on through Canvas or maybe on the GroupMe chat, and I'll correct it. So I'll correct this one right after the class. Okay. Thanks for mentioning that. Yes.
Verify with the G trying conducting.
So yes. All right. So as we were discussing in one of the previous lectures, that gain just means output over input. Gain does not mean it's a voltage gain or current gain or time gain or whatever. It could be anything. Gain depends on what your basically the unit of gain depends on what your output quantity is and what your input quantity is. If your output quantity is a current and your input quantity is a voltage, then your gain is current over voltage, right? And current over voltage is conductance. Right? Just like voltage over current is resistance, Current over voltage is called conductance because conductance is 1 upon resistance. Yeah. So GM represents conductance, and that's it.
And like theoretically, if there was a third resistor in between RO and R2,
So let's say you place something here.
you do like a split transformation between the dependent current source and RO. You do a split transformation.
You can do a source transformation, yes. So again, you have learned multiple techniques. Whatever is easier for you, do that. But you'll see whatever technique you follow, your final answer will be same. Question? Uh-huh. Uh-huh. Yes. Yes. So here, of course, your input parameter is a voltage. But of course, because this is a current, it has to be in ampere. Current cannot be anything else, right? Yes. Yes, exactly. Exactly. Okay. Now let's, we have maybe 5 more minutes. So let's discuss a little bit about amplifiers, and we'll continue these discussions in the next lecture as well. Now, some of these things we have already covered, so I'll not repeat things again. But very basic things, the job of your amplifier is to amplify or increase the input AC signal. Again, amplifier does not and cannot and will never increase the DC value of a signal. It can only amplify AC signals. Okay. All right, and where would the extra energy come on for the amplification? That comes in because you have a supply connected to it and you can draw energy from the supply. That actually provides you more energy for the amplification so that you don't violate energy conservation laws. Because you can never violate physics, right? Whatever circuit we learn, eventually it's physics. Okay. Amplifiers input and output characteristics. This is an important thing to learn and remember that, let's say you, what this curve is generally called a voltage transfer curve or a transfer curve. Again, why is it called a transfer curve? Because you want to transfer, you want to find out the transfer function from the input to the output. If your input voltage is V in and your output voltage is V out, you want to find out how does your output voltage V out change as your input voltage is changing. And that is the transfer function, output as a function of input. And this curve, now the representation of the transfer function in graphical domain, that's this curve. And this curve is called the transfer curve. And more specifically, because this is voltages, voltage out versus voltage in, this will be called the voltage transfer curve. But in general, it could be any transfer curve. It could be current transfers or transconductance transfer curve and so on. But if it is voltage versus voltage, it's going to be called a voltage transfer curve. All right. Now, usually these input and output signals are represented in voltage. And at any instant of time, this snapshot of the input and voltage, output voltages or currents is going to be called an operating point of the circuit. Right? So you may hear about this term later on in your circuit courses, operating point. What does operating point means? Operating point means that what is the voltages or what is the currents that is present in the circuit at any particular time instant t. And that voltages and currents can change over time if you are dealing with an AC signal. If you're dealing with an alternating signal that itself changes with time, the circuit's operating points may also change slightly with time. There would be more deeper concepts related to that. But right now, let's just understand what does the operating point means. And it means that whatever voltage, whatever current you're operating your circuit at. All right. Now, as you see here in this particular curve, again, we'll discuss more that why your V out first stays constant and then reduces a little bit, then starts reducing faster, and then eventually reaches to a constant value again. We'll discuss that why does that happen. But for any amplifier, we'll learn something called a common source amplifier in very much detail in the course for MOSFETs and so on. Even your amplifiers in general will have this kind of a voltage transfer characteristic. We'll go into detail. So save that why question for later, that why does the curve look like this? And come back to me and ask me that question if I don't explain it in the class, maybe within the next 2 or 3 weeks. Okay. But let's just assume that the curve looks like this, that, okay, initially so this is the point when your V in is 0 and then you're increasing your V in, input voltage. Your output stays constant And then your output starts decreasing, and then eventually your output goes to 0 when your input is very high. So input and output, as you see, has a opposite relation, inverse relation. Why is that? We'll discuss that I'll try to discuss that in the next lecture, because that will take some more amount of time to understand. But what is the slope of this curve? Think about the slope of this curve. What is the slope of this curve? Your y-axis is V out, x-axis is V in. dV out over dV in, what is that? That is gain, right? Any small change in the input voltage and any small change in the output voltage, the output to input ratio is the gain. What is the value of the gain in this circuit when the operating point is here? Output voltage is constant. Here also output voltage is constant. If your dV, so let's just write that down, dV out over dV in, that's basically your slope, right? And that slope is your gain. Let's just call it gain A, because this is voltage right now, V out over V in. So that is your gain A, and that is going to be your slope. Where is the slope highest for the curve? The slope is highest when it is falling fast in this region, right? So this is the region where your slope is highest. Your slope is 0 over here. Your slope is also 0 over here. And that gives you a sense that, okay, my amplifier may not amplify as much as I want if I'm anywhere in this curve. Yes. Absolute value, yes, you can call it the absolute value sense I. We'll discuss that more, because I understand where you're coming from. You're saying that because V out reduces with V in, my gain is negative, right? But what I'm saying, high gain is the absolute value, and where your slope is highest, you want to be at that point, right? Because if you want gain and you want maximum gain, so you want to be at that point where the slope is highest on this curve, and the slope is not same at every point on this curve. And that gives you an idea that let's sleep on that idea, and then we'll come back later in the next lecture, that where does your amplifier need to be biased at? It cannot amplify with the same amount of gain everywhere. If you want gain, you have to bias it at the middle of this voltage transfer curve. Okay, let's stop here. We'll discuss more in the next lecture. Yes.